This is example 5, where we are asked again to find yn, but this time with non-zero initial conditions. So we are given a difference equation like this, but additionally we are also given the value of y minus 1 as well as y minus 2. Whereas y minus 1 and y minus 2 are here, it means that they did not start with the zero initial condition. They have these values for y minus 1 and this value for y minus 2. The input is a causal signal 2 to the power of minus n. So the difference between this example and previous example is the initial conditions given to us. We must take this into account when we are solving to find yn using z transform. So we begin to find the z transform of yn is yz. What about yn minus 1? Yn minus 1 will have actually z minus 1 yz. However, because our initial condition is not 0, we must add this term y to the power of y at time minus 1. And again, we'll z transform yn minus 2. We have actually z minus 2 yz plus z minus 1 y of minus 1 plus actually it will be z minus 0 y of minus 2. Since z minus 0 is 1, so it is simply y minus 2. So you will see that the initial conditions must be included into the z transform. If we do not include this initial condition into the z transform, then you are actually solving a difference equation with zero initial condition. In this example, this will be wrong answer because the initial conditions is given to us. Alright, now let's find the z transform of the causal signal. It is this, and therefore you can work it out, and the answer is z over z minus 0.5 is a z transform. Now, because this is the causal signal, it has no past value, therefore the z transform of xn minus r is simply this. There is no plus all these things here, as in the previous illustration for yn, because though this has the initial conditions, while this guy does not have, because this is a causal signal only. We are now ready to plug in all we have find into the z transform representation of the difference equation. So this is the first part from yn. This is from yn minus 1. This is from yn minus 2. Here is from here is from 3x of n minus 1, and here is from 5 of x of n minus 2, as you see on top. So let's zoom in. Now look at this equation carefully. This is 3 over z minus 0.5. The numerator z is gone. Look at this expression of xn. It is z over z minus 0.5. This is xn. The z transform of xn is z over z minus 0.5. If I'm delayed by 1, then it is 1 over z times this guy. So the numerator z is gone in this expression here. And this is xn minus 2. So we introduce a 1 over z again for this expression. The 5 comes from the constant multiplied by xn minus 2. Alright. We're now ready to manipulate and get the yz's together. So this is the yz we are interested in. And you start to shift the polynomials of z's such that you can get y of z into some expression which allow us to perform partial fraction expansion. Again, the trick is to make the left hand side to be yz over z when you are doing the partial fraction expansion, because later on we have to move the z to the right hand side again, such that the z transform table of that partial fraction exists. So later on you realize that this z will be moved here such that we can do the lookup table. That's the idea. Now, of course, manipulating all these polynomials and rational functions is very error prone, so you please go and check your answers with respect to mine over here. The final partial fraction looks like this. So there are 3 parts, and since there are 3 parts, each of these will generate a exponential. So this is the final answer. So the last part is really easy. Once you can get the partial fraction expansion, then each of these individual expressions get into an expression that looks like this, with the constant being maintained like here. Okay, with that we end our discussion for finding yn with non-zero initial condition. Thank you.